Well, welcome to the last video of chapter 14, and this will be QOD number 32. And this is going to talk about the effect of two things on the rate of reaction: temperature, and also the effect of what's called the activation energy on the rate of the reaction. And so if we think about the effect of temperature, so here's a glow stick. And a glow stick works by what's called chemiluminescence, which is there's a chemical reaction that actually gives off energy, visible light, as part of the reaction. And so if you put a glow stick into hot water, it will glow really bright. If you put it into cold water, it will not glow as bright. And that's because the reaction is going slower in the cold water, and therefore it's producing less light. Your glow stick will last longer because it's got a finite amount of material. And in fact, when I used to work at an amusement park when I was a teenager, they would sell these things out of like a dry ice box. So they kept really, really cold until somebody bought them and put them around their neck. They used to sell glow necklaces. And then it would start glowing when you took it out of the dry ice because it was warming up. And so it's generally the case that as temperature increases, the rate of the reaction increases. Now, if you think about what would cause that to happen in terms of a rate law, you're not changing the concentration of any of the reactants by warming them up. And therefore, the only way the rate could be going up is if you're increasing the value of K with temperature. And in fact, here's a typical graph of that's plotting the value of K for a first order reaction against temperature. And you can see that this does this in an exponential way. That K increases with temperature. So in order to think through why this is, we want to talk about it just kind of a little bit more formally than we have so far, what's called the collision model of reaction. We've talked about this, but let me just do this in a formal sense in a video. In order so in a chemical reaction, we're going to make bonds and we're going to break bonds. And in order for that to happen, generally two reactants are going to have to collide with each other. Unless it's a unimolecular step, you're going to have reactants colliding with each other. And so they can only react if they collide with each other. And so let's take a look at an elementary step. It's actually on the next slide, but I've just written it out for you here, in which a molecule of NaCl collides with a chlorine atom, which is not a stable intermediate. So this would be the second or third step in some mechanism. It's an elementary step. We give a molecule of NO plus a molecule of Cl2. And so here's an example of what would result in a successful collision. Because the products I'm trying to make are Cl2 and NO, the Cl atom that's coming in has to collide with this Cl-NO molecule in the right way so that the two chlorines are bonded to each other and kick out the NO. So this would be a successful collision. This would be an ineffective collision because the chlorine is not colliding with the other chlorine, it's colliding with the oxygen here. And so they have to collide in the right orientation. They also have to collide with sufficient kinetic energy to cause the reaction to occur. If they just kind of happen to bump into each other, they're just going to bounce away. They have to collide with the right orientation and with enough energy to cause the bond breakage and formation to occur. We call that minimum kinetic energy required for that reaction to occur the activation energy. And so, in other words, there is a minimum amount of energy required for the reaction, and we quantify this on a per mole basis. But it's called the activation energy, and we use E subscript A is an abbreviation for activation energy. And so just so as if a ball can't, well, I'm not even going to read that. I'll just show you. Here's a picture of, I tried to decide who in our class this guy looked the most like, and I decided he looked the most like me. But if there's a hill between where you're putting and where the hole is, and this is a little bit exaggerated unless you're playing at a miniature golf place, even though you're standing on the same level as the hole, you still have to hit it with a certain amount of energy to get it up and over the hill. And that's also true with a chemical reaction. The reaction may be exothermic or exergonic, that is, the products are lower in energy than the reactants, but there's always some activation energy barrier that you've got to get the reaction up and over. And so let's take a look at how that would appear in what we call a reaction energy diagram. Because up until now, we've really just thought about reaction energy diagrams like this. The question is, are the products lower in energy than the reactants? If they are, then we would call the reaction like this one exothermic, or if we were, instead of delta H, we were measuring delta G, we would call that exergonic. And if it was going the other way, then we'd say it was endothermic or endergonic. But all we were doing was looking at the difference between the energies of the reactants and the products. We were not looking at how they get from one location to the other. To get from one location to the other, we use what's called a reaction energy diagram or a reaction coordinate diagram. Because now, instead of being a one-dimensional thing, which this is, it's just graphing energy of the reactants and the products. This is actually graphing the energy of the system over the course of time. Now, this difference between the energy of the reactants and the energy of the products corresponds to just this distance in a diagram like that. The difference is, this is showing you that in order to get from here to here, it actually has to go over this hump, which we call the activation energy, and then slide down the other side. And so we've talked a little bit before about, okay, if you had to get to the lunchroom for your lunch, but you had to climb over a wall to get there, that the higher that wall is, the slower the rate of kids getting into the lunchroom would be. The lower the wall is, the faster the rate of kids getting into the lunchroom. And this diagram actually helps make the point that there is that thermodynamics, that is whether or not a thing is spontaneous and will occur spontaneous, and kinetics are two different things. It's the difference between the reactants and the products that determines whether a reaction is spontaneous or not. It's this difference, and that's the delta E you see here. It's the difference between the reactants and the top of this curve that is the activation energy that determines the rate. And those things are independent of each other. Let's look just a little bit more closely at this diagram. It shows the energy of the reactants, which I've labeled here as A plus B. It shows the energy of the products, which I've labeled here as C plus D. And therefore, we can calculate the delta E here. I would generally think about this as being delta G, the free energy difference between the reactants and the products, which tells you whether or not the reaction is spontaneous. The highest point on the curve, the highest point on the diagram, is what's called a transition state, and it doesn't correspond to a particular species. You don't want to confuse a transition state with a reaction intermediate. It's just that place along the curve in which bonds are being broken and bonds are being formed, at which the potential energy of the system is the highest. It doesn't correspond to any specific structure or any specific discrete molecule. It's simply the place in the process of breaking old bonds and forming new bonds where the potential energy of the system is the highest. And that energy gap between the reactants and the transition state is called the activation energy barrier, or just the activation energy. You can see I've got it labeled here as E sub A. Okay, well, let's think about why there is an effect of temperature on the value of K. If, by the way, for a given reaction, these things are constant. The energy difference between the reactants and the products are a constant. The energy difference between the reactants and the transition state is a constant. And so how can K change if these values all remain constant? Well, let's take a look at what's called a Maxwell-Boltzmann distribution. And we talked about this before, back when we were talking about various URMS and U average and U most probable for gases, that there is a distribution. This time the x-axis isn't speed, it's kinetic energy, but remember that kinetic energy is a function of speed. It is the function of the square of speed. So at a lower temperature, you're going to have, you still have a large distribution, but it's a little bit, everything's a little bit closer together. At a higher temperature, the average kinetic energy gets higher, and the whole thing sort of spreads out more. And if we just say that, okay, this place, when it comes to kinetic energy, indicates the height of the activation energy barrier, that is the minimum amount of energy required for the reaction to occur, then anything that is on the right-hand side of that dashed line is a molecule or molecules that have enough kinetic energy to overcome the activation energy barrier and for the reaction to occur. And if I increase the temperature, you'll see that a larger fraction of the molecules in the sample now have energy at or above the activation energy. The temperature is the average kinetic energy of the molecules in a sample, but you can see that that is distributed. They don't all have the same kinetic energy. There's a wide distribution, but at higher temperatures, more molecules, a larger fraction of the sample has energy at or above the activation energy barrier, and therefore you're going to increase the rate of the reaction and increase necessarily the value of K. We can actually come up with a mathematical treatment of what fraction of molecules have energy above the activation energy barrier. And so this is F is the fraction of energy, fraction of molecules with that energy, is E, that is the base. Remember, E is the base for a natural logarithm. It's like 2.72 or 2.82, I can't remember exactly, to the power of negative EA over RT, where R is the gas constant and T is going to be the temperature in kelvins. So if you think about this for just a second, this is a negative exponent. So the larger this number is in magnitude, the smaller F is going to be, right? Because that's a negative exponent. So this is a really very negative number, then F is going to be small. If this is a less negative number, F is going to be larger. And so when temperature goes up, because it is in the denominator of this exponent, that's going to make the exponent smaller. A higher temperature will make this whole term of a lower magnitude. Because it's negative, that means it's going to give me a larger fraction. If temperature is low, then this whole thing is going to be a higher magnitude of a negative number, and that's going to make my fraction a smaller number. So there is an inverse relationship here. The higher the temperature, the smaller the magnitude of this, the greater the fraction. The lower the temperature, the greater the magnitude of this term. Because it's negative, the smaller the fraction. We can further take that whole thing and turn it into what's called the Arrhenius equation. And we're going to be just talking about the Arrhenius equation here for a few minutes. And so what the Arrhenius equation says, this is defining the relationship between K, activation energy, and temperature. K is the rate constant for a given reaction. T, as we were just saying, is the temperature in Kelvin. EA is the activation energy. R is the gas constant. A is what's called the frequency factor, and what the frequency factor represents is essentially it's related to the number of collisions that will result in having the proper orientation for reaction. It's not the number of collisions, it's not how frequent things collide, it's not how frequently they react, it's the frequency of, it's the fraction of collisions that is going to result in an effective collision, an effective orientation. Okay, let's take a look at some mathematical manipulations we can do with the Arrhenius equation. The first and simplest, because we don't really like things with the base, we don't really like exponential functions like this. So the way to get rid of that is to take the log of both sides. Oh, let me just give you some simple important takeaways from the Arrhenius equation. For a given reaction at two different temperatures, the value of K is going to be greater at the higher temperature. And I was just talking through that earlier with that fraction. But as temperature increases, the magnitude of this exponent decreases. Because it's a negative, a decreased exponent is going to mean a larger value for K. As temperature decreases, the magnitude of this whole exponent increases. Because it's negative, K is going to be smaller. So higher temperature, bigger K, lower temperature, smaller K. The other important thing is this. at a given, if we hold temperature constant and look at two different reactions that have two different values of EA, the bigger the value of EA, the smaller the value of K, which makes sense. Higher activation energy, reaction's going to go more slowly. Bigger exponent here, because it's negative, K is going to be smaller. If I've got a lower activation energy, we would expect the reaction to go faster. Lower EA, smaller exponent, because it's negative, that's going to make a smaller exponent is going to make K larger. Okay, we can take the log of both sides of this. So we go and we take the log of this side, it gives us the log of K. Log of this side gives us the log of A minus EA over RT. Okay, so it's the log of A minus EA over RT. And here we can actually put that into a linear form in which Y is equal to the log of K, X is equal to reciprocal temperature, the slope is equal to negative EA over R, and the y-intercept is equal to the log of A. And you can see you get a linear relationship when you plot rate or K, log of K versus reciprocal temperature. We're not going to do plots like that. Let me show you a much more valuable way of using this equation. And that's simply to say, let's take this thing that we just had here. Log of K is equal to negative EA over R times reciprocal temperature plus the log of A. And I'm going to say at temperature 1, I've got K1 and I've got temperature 1. Remember, K varies with temperature. So at a given temperature, we'll call that K1, and we'll call the corresponding K, K1. Now I've got a second temperature, I'll call that T2. That's going to lead to a different value for K. We'll call that K2. Well, really what you do when you're trying to find the slope of anything is you subtract one point from another, so you're calculating rise over run. So I'm going to subtract this equation from this equation. That means on the left-hand side, since I'm subtracting the bottom one from the top one, that gives me log of K1 minus log of K2. On the right-hand side, it gives me negative EA over R times reciprocal T1 plus log A. Then subtracting a negative will give me positive EA over R reciprocal T2 minus log of A. Well, now I can just do a lot of, in the last step, gathering, canceling things out, gathering up, and factoring things. Log of A minus log of A simply is equal to 0, so that can go away. EA over R is a constant, so I can simply factor out negative T1 plus negative reciprocal T1 plus reciprocal T2, which is the same as 1 over T2 minus 1 over T1. And as you'll recall, the log, when you subtract the log of B from the log of A, that's equal to the log of A over B. And so this side becomes this side with the log A's canceling each other out and the EA over R being factored out gives me this. And now I've got a really valuable equation, actually, that allows me to do a couple things. If I can calculate the rate constant for a given reaction at two different temperatures, so I look at the value of K at, say, room temperature, and then I look at the value of K again at some elevated temperature, I can plug those four variables into this equation and calculate the activation energy for the reaction. And we're actually going to do that in the iodine clock experiment. If I know the value of the activation energy and I know the value of K1 at some given temperature, then I can calculate the value for K at some second temperature using this equation. So this is a pretty spiffy equation, and we'll take a look at this in class. Let's just finish up by talking about catalysts. So a catalyst is something, as we said before, that increases the rate of a reaction without being consumed. Now, it's going to have to do that by increasing the value of K, but it doesn't do that by increasing the temperature. So how is K going to get larger if we're not increasing the temperature? And the answer to that is a catalyst works by lowering the activation energy barrier. And so it changes the mechanism So here's the uncatalyzed reaction in the red. If I put it, and that's just watching, in this particular case, they're talking about just watching hydrogen peroxide decompose into water plus oxygen. That will happen very, very slowly on its own. It has a high activation energy, so it happens very slowly. If I put a little bit of bromide ion, some HBr in here, that creates a new pathway in which the total activation energy is lower than the activation energy of the original reaction. It's a new mechanism with a lower activation energy and therefore a greater value of K. Let's think about something that we actually did in class. Here's the iodine clock reaction, and we've talked about this in class. That the first reaction is the reaction of persulfate and iodide to give sulfate and iodine. And then the second reaction was iodine plus thiosulfate to give this tetrathionate plus regenerating the iodides again. So when we add this up, we get this reaction. Persulfate plus thiosulfate gives sulfate plus tetrathionate. We talked about the fact that iodide is acting as a catalyst here. And so iodide is being consumed in the early step and regenerated in the second step. These two reactants will react with each other on their own, but this reaction will take days to occur. If we put some iodide in, which is what we did in that iodine clock reaction, then this thing happens in a matter of seconds or minutes instead of happening in a matter of days, because this is providing an alternate mechanism whose activation energy is lower. And so the uncatalyzed reaction would simply be, in this case, would be the persulfate plus thiosulfate to give sulfate plus tetrathionate or tetrathionide. I'm not sure what its name is. The catalyzed reaction with the iodide in gives us a different mechanism with a lower activation. Now we can play a similar game with the Arrhenius equation that we did before, which is simply, instead of looking at different values for K at different temperatures, we can look at different values for K at different activation energies, this being the uncatalyzed and this being the catalyzed. Now temperature is constant. I'm not going to dwell on this very much because I want this video to be over, as you do. But now we get a new equation in which the log of K1 over K2 is equal to 1 over RT times the quantity EA2 minus EA1. So if we know, and this is an experiment you can do, if you know the value of K and you've calculated the activation energy at a particular temperature, which we do in the iodine clock reaction at room temperature, then you can run the reaction again at a different. You can run the reaction again in a catalyzed form, and I'm sorry, this is uncatalyzed catalyzed. You can run the reaction again in a catalyzed form, see how much faster it goes, and you can calculate the difference between the activation energies for catalyzed versus uncatalyzed. Okay, quickie to remind you that enzymes are biological catalysts, and so they don't function in this way of being consumed in an early step and regenerated in a later step. They actually have the job of bringing reactants together in just the right conformation to react with each other. And that's how enzymes tend to speed up reactions. Okay, what you really want to know is what's going to be on the QOD, Mr. Jones. And so here we go. 4 things that you should really, 4 skills that you should have coming out of this video. Understand the basics of collision theory. That is, you need to have sufficient energy and you need to have proper orientation in order for a reaction to occur. You need to be able to interpret a reaction energy diagram. Where are the reactants? Where are the products? What would be delta G for the reaction versus what would be the activation energy for the reaction? Also need to know where the transition state is located. You need to be able to interpret the Arrhenius equation. Those T1, T2 equations I was showing you, or EA1, EA2, you don't actually need to be able to do that math for the College Board, but you do need to be able to look at the Arrhenius equation and say, what this means practically is as the magnitude of EA goes down, the value of K goes up, or as the temperature goes up, the value of K goes up. And then finally, just understand in general terms how a catalyst speeds up a reaction. Okay, we've hit 25 minutes. This is longer than I thought it was going to be. Check out the practice problems that I have posted along with this video, and thanks as always for watching.